First off, what are descriptive statistics describing? Unless you have the mind of God, your statistics are describing a sample, which is a group of things, subjects, or events, or cases selected from a larger group, in the hope that studying this smaller group, the sample, will reveal important things about the larger group, the population, from which they were taken. So the population is therefore the entire collection of things, subjects, events, or cases in which you are interested, or to which you would like to generalize, or about which you would like to make predictions or decisions. Whether your data constitute a sample or a population depends on your question. When I report the mean and standard deviation of test results to students, those statistics, the mean and standard deviation, are population statistics, because I only care about the students who took the test, and I have the data for all the students who took the test. If, however, I wanted to use that same data to see what students typically score on that test, what I would expect the next group of students to score, or a student who hadn't written the test yet might score, then those very same data would become a sample. In the first case, the case of just reporting the results to students, I would use the population formula for the standard deviation. In the second case, where I am attempting to predict new values or generalize to one or more unknown cases, I would use the sample formula for the standard deviation. Why? The sample formula, by reducing the denominator, makes the spread estimate larger, which adjusts for the fact that the unknown things, subjects, events, or cases in the population could reasonably be expected to be more variable than whatever limited sample I have. In the population case of reporting my results to students, I do not need to pretend that there was more variation than there in fact was. But in the sample case, where I do not have all of the data, I should anticipate that the world, the unknown or unobserved cases, has at least a bit more variability than my sample of it. So whether your data set and whether your statistics, i.e. your statistical results, are a sample or population, and whether you therefore should use sample or population formulae depends on what you intend to do with those results. Note that in practice, nearly all statistics reported are sample statistics, in part because all the software defaults are sample. SPSS, R, and the idiosyncratic custom software that I've interacted with all use sample standard deviation formula, unless you force them to do otherwise. This caused a bit of a headache the first time I taught undergrad stats because I used chapters from actual mathematical statistics textbooks from the 70s, which do a far better job of actually logically explaining the mechanics of things than the newer books or the social science ones. But the statisticians teach based on the capital T truth of population statistics. So when you checked your hand-calculated work with whatever software you used, the results would be off by whatever difference the slight overestimation of variation made. It was a problem that did not scale well into higher-order statistical moments like kurtosis. Anyway, let's assume our data are a sample. Ideally, they would be a random sample. A sample for which every subject or case in the population had an equal chance of being selected. Let's hear that definition again. A sample for which every thing, subject, event, or case in the population has an identical chance of being selected. I would like to know how Canadians feel about their healthcare, let's say. I have a survey. I can only obtain a truly random sample then if every person in Nunavut has the same chance of being asked the survey questions as a given person in Toronto, and if every given person in Toronto has an equally likely chance of being selected. Graduate students, dock workers, new immigrants, and neurosurgeons. If it is a sample in the social sciences, then it's not a true random sample. Feel free to comment with any exceptions you can think of. A popular textbook by Howell has 2 quotes in the first 3 pages, and these are on page 2. Truly random samples are normally very impractical, if not impossible. So flip to page 3. To the extent that the sample is not random, our estimates may or may not be meaningful, because a sample may or may not accurately reflect the entire population. Putting these quotes together, as reasonable people who are reading might, what we do normally may not be meaningful, and may not accurately reflect the entire population. We are not even 3 pages in to the study of statistics, and there already seems little hope Truth is just the illusions of the powerful. The matrix cannot be escaped, and universities teach statistics just to flaunt their power and torture students.
Maniacal laugh. Maniacal laugh. Maniacal laugh. Maniacal laugh. Maniacal laugh.
Maybe. But if you look at stats like a tool, like a pragmatist, then the non-randomness of samples would be akin to imperfect measurements that we make, and the imperfection in the cuts and the alignments that we have. Measure twice, cut once becomes a call to replicate your findings before applying them, before cutting into the real-world wood with them. Problem solved, right? No! Problem made worse by the fact that we think we've solved it, but we'll circle around to that later. Okay, what's wrong with not having random samples? Well, external validity is the extent to which the findings of a study are relevant to the subjects and settings beyond those in the study. The more common word, in my house at least, is generalizability. I really don't care about most psychological research because it's done on undergraduates and tends to dramatize tiny differences. Even if big differences were found, the researchers have all their work ahead of them, even just to show that the results apply to non-university attending people of the same age. Never mind the fact that the cohort from 3 years ago may differ from the one that I want to apply the finding to now. Our pretending that the study or sampling of undergraduates is a contribution to knowledge is infantile pretend play and cannot be defended.
No, it's beneath that level. It's frighteningly beneath it. It cannot be defended.
Generally, the term external validity is used in order to contrast it with internal validity, which has more to do with one's measures. Internal validity is the extent to which the results of a study, usually an experiment, can be attributed to the treatments or groupings rather than to any flaws in the research design. In other words, internal validity is the degree to which one can draw valid conclusions about causal effects of one variable or another. This depends on how well the quote-unquote extraneous variables have been controlled by the researcher. Keep in mind that a variable is anything that changes, anything that can take on different values, whether we're measuring it or not. An extraneous variable, also called a nuisance variable, is any condition not part of the study, anything in which the researchers have no interest, but which could have an effect on the study's dependent variable. Researchers usually try to control for extraneous variables by experimental isolation, randomization, or statistical techniques like analysis of covariance. Not extraneous are dependent variable, the one that we think depends on the values of other variables, and the independent variable, the one we think causes, predicts, or explains changes in the dependent variable, and which we are observing or creating a difference in to see if this influences the dependent variable. My preferred term for the dependent variable is outcome variable, and my preferred term for the independent variable is predictor variable. Now that we have some formal names that tell us something about our study design and intentions, we need some names for our types of measurements that we will be or have been employing. Scale refers to the units of measurement used to capture or record a variable. Your scale is discrete if it has very few possible values, like a Likert scale, or if differences between the values are not uniform or consistent. For example, if we are moving from right to left on the political spectrum in Canada, the difference between voting for cons and libs is not the same as the difference between libs and NDP. Discrete scales can be nominal, meaning they have no natural or necessary ordering. For gender, you could have male be 0, 1, or 2. The number's arbitrary. For country of birth, you could code Canada as any arbitrary number. Discrete scales can also be ordinal, meaning the values have a natural or necessary order, but there are few values and or the difference between those values is not uniform or consistent. The difference between first and second place in a race is not necessarily the same as the difference between second and third place in that same race, in terms of the time between them, in terms of the points that you gain by finishing in that place in the race. The difference between a private and a corporal is not the same as that between a colonel and a brigadier general, even though there is only one ranks difference between them. Discrete ordinal scales would be where Likert-type scales belong, even though it's not difficult to find research that treats Likert-measured variables like continuously measured variables. This is something that annoys statisticians and gives them ammunition for rants against psychological research as infantile pseudoscience. Thank you, sir. May I have another? The general attitude toward this criticism is an acknowledgement that our measures and concepts are so fuzzy anyway, and we promise not to pretend our work is important, so why not just treat it like a continuous variable? But really, the stronger argument here would be a tukukwe ad hominem type of rebuttal. This is the two wrongs fallacy, the pot calling the kettle black fallacy, the look who's talking fallacy, like this. All measures being analyzed are arbitrarily discrete. If a statistician is computing something, that means measurement has stopped. Maybe at the tenths column, maybe at the ones column, maybe at the tens column. The measures are not infinitely precise, and measuring at a higher value is like rounding to a higher value. It doesn't make the variable any less worthy of continuous variable status. Not bad, says the statistician. But the analogy doesn't work. With Likert scales, we're endorsing statements, not just selecting from a scale. If it can go on an analog choose-your-own scale, then sure, round to whatever high values you want. But as long as the verbal options have a chance of their differences not being uniform or consistent, the scale is discrete. Continuous variables are those measured on either an interval or a ratio scale. For continuous variables, differences are uniform and consistent, i.e. the difference between having 3 siblings and having 4 siblings is the same as the difference between having 2 siblings and 3 siblings. It's 1 sibling's difference. Note that counts are continuous, even where you cannot have a fraction of a thing. But whether we want to treat them as continuous is up to us. If you only have 4 or 5 different values represented in your data set, you may not want to treat them as a continuous variable. Interval scale continuous variables are those where 0 does not mean the actual absence of the thing being measured. If I make an extroversion scale where positive values are extroversion and negative values are introversion, then a 0 on that scale is not the absence of the trait, it is a score on that trait. The ratio scale is one where 0 does mean the absence of a thing. 0 seconds, 0 siblings, 0 inches between the target and projectile, etc. These units are one of the most important determinants for when we are planning out our data analysis, the types of questions we can answer, and the tools we have available to answer or ask those questions. These scales will determine the units in which our descriptive statistics get reported. Descriptive statistics are summary numbers that describe characteristics of our distributions. Distributions come in a variety of shapes, and we wish to work with summary numbers that are sensitive to these shapes. The image here shows us 8 different distributions. A and B have identical shapes, but the numbers in B are greater than those in A. The technical jargon is that A and B differ only with respect to their central tendency. Distributions C and D differ from each other in that C is more widely dispersed than D. The distinct values in distribution C have a greater range than those in distribution D. Distributions E and F illustrate skewness. E slopes more gradually to the right and is therefore a right-skewed distribution, or positively skewed distribution. F slopes more gradually to the left than to the right, so this is a left-skewed or a negatively skewed distribution. Finally, distributions G and H are designed to illustrate what's known as peakedness, or kurtosis. G is rather flat compared with H, since H has a more pronounced peak on the distinct value 4. Circling back to the not a true random sample problem, now that we've seen some distributions and experienced being tempted to think that shape and central tendency that we have generalizes to whatever population we want it to, the language we use tends to be that samples are models of the population or the relations in it. This could be taken as meaning that we think that we can know what the population looks like from the sample, but I prefer to add the idea of severe testing here, or an idea from severe testing here. Let's say that the only point of statistical testing is to give the most severe possible test of your idea that you can. In other words, The test is to see whether your hypothesis, your idea, can survive exposure to reality, to as harsh a possible reality for your idea as possible. You test it where it's least likely to be found true, and the more it survives testing, the more likely it is to be true. Let's take this model as our approach. Now let's say we have two options. We can interpret our research in terms of the larger population to which ideally we would like to generalize, or we could interpret our research in terms of generalizing only to cases that are like the cases that we have in our research. So we're limiting ourselves and our interpretation. Let's take these as our two options and see how they fare. Under interpretation 1, we just don't have a severe test, because if the test fails, then we can blame that failure. We can blame the failure of our hypothesis on the imperfection of the sample. Well, maybe the sample doesn't represent the population to which we want to generalize, so we've learned nothing. If the test leads our idea to survive, so say we get statistical significance or the difference that we wanted, this still doesn't make things generalizable. So again, we haven't necessarily learned anything. Under interpretation 2, which is the model, the interpretation to actually test what we want to test. The interpretation 1 is just kind of the, let's see what we think the larger population looks like based on looking at our sample. And we already know that the larger population doesn't look like the sample, so we're running around in circles. So under interpretation 2, we have the ability to actually interpret the failure based on the power of our study. If we have a low-powered study, then we can't really interpret a failure. But let's say we have a well-powered study, we can interpret failure to a limited extent. And if we survive the test, if our idea survives the test, then we have actually conducted a severe statistical test, and we can make a conclusion based upon that, or a generalization based upon that. If something doesn't work for your model, then it is less likely to work if you try it again on another sample from the same population. This logic holds up better than the model to see what it looks like idea, because all of the fuzz in the measurement and sampling would go towards saying one is wasting one's time trying to see what the population looks like from such imperfect sampling. But in the case of testing a sample, a failure is relevant and informative, even where a success might not be. Here you could say, I tried it once and it didn't work, or, well, the model flew. In other words, version 1 says the population looks like this, or there is a difference if we obtain statistical significance. If significance is obtained, responses will vary though. Version 2 says this model did not fail, or tried and tested if we obtain statistical significance. If no statistical significance, then we could say, well, it's not useful here. It doesn't appear to be useful here. Might be the correct or appropriate conclusion. Either way, the same work is being done, but version 2 doesn't make silly appeals to the capital T truth about some abstract population that it has to apologize for not perfectly mirroring, i.e. for not having a true random sample of it. Rather, this version, version 2, invites you to imagine the population that whatever sample you have would actually look like. So for example, the most appropriate population for a sample of 10 psychology graduate students from Trent University would be psychology graduate students from Trent University. You can then say either the model works here or it fails here, and what that means for the model elsewhere is open for speculation. It simply wasn't tested elsewhere, and to pretend it was somehow almost tested in the broader population is just that, it's pretending. While we approached this in an overly theoretical way by splitting hairs regarding how to interpret what the model is for, it boils down to simple advice regarding reporting and conclusions. For honesty, accuracy, and to be an adult about one's work, lead with the properties of your sample and what it means. What those properties mean. If enough people with idiosyncratic samples find the same thing, maybe we could then build a case for the capital T truth about populations they all belong to, but not before then, not without true random sampling, which we never have. Next lecture, we'll be putting these models, these distributions to work with very simple t-tests to round off the review section of this course. Meanwhile, here is your R content for this lecture.